In 9.3a, we worked on finding points of discontinuity, and we found those by setting the denominator equal to 0. So another word for that is finding the zeros of the denominator. So when we did that, it gave us the points of discontinuity. So that's the first step of what we're doing today. It's just identify where the points of discontinuity are. Then after that, we have to figure out what type of discontinuity they are. So we have two different types of discontinuity. We have vertical asymptotes, which are lines that the graph gets like really, really close to but never actually touches. Okay, they might look like that. That's just an example. And when you look at that in the table, say this is at -3. It'll have a number for -4, number for -2, and then it'll say error at -3. The other type is a hole. For graphs that have holes, they look quite normal. Okay, I'm just making this up, except that they jump over a spot. Now the problem with these is that on the calculator, you can't actually even see the hole. It just looks like the graph keeps going. That's because the calculator graphs so like microscopically that the actual point, like say it's -3, is just tiny, 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 so you can't actually see that they jump over it. But if you look in the table, same thing will happen again, where at -3 there will be an error. So holes, the graph looks totally normal on the calculator, but there's an error at whatever the point of discontinuity was. Now, asymptotes, they have like extreme behavior. They go way, way up or way, way down. Okay, so that's when you know it's an asymptote. If it doesn't have extreme behavior like that, then it is a hole. Now, how do we know from the equation whether it's vertical asymptote or a hole? Well, we can partly figure it out, and that's by looking at the zeros of the numerator. If zeros from the numerator are common with the zeros of the denominator, so they have the same, then we have to look at the graph because we don't know whether it's a hole or a vertical asymptote. So really, if they're the same, that doesn't really help us any. We just have to graph it. If they're different, if they don't match, then it's automatically a vertical asymptote, and you don't have to graph it. So that's the really nice part, is that when they don't match, you don't have to graph it. So let's look at this in some examples. So step 1, looking for vertical asymptotes or holes, is to set the denominator equal to 0. So x minus 2 and x minus 3 equals 0. So let's see, x minus 2 equals 0 and x minus 3 equals 0. So what are my zeros of this equation? Where does it cross the x-axis? X equals 2, x equals 3. So those are points of discontinuity. We know the graph doesn't touch those points, but we don't know if it's an asymptote or if it jumps over it because it's a hole. So we have to figure that out. We have to figure out the type. So set your numerator equal to 0. So we have x plus 1 equals 0, which makes x equal -1 when you move it to the other side. Does that match either of these? No, it is not the same. No match means vertical asymptote. So your answer would be vertical asymptotes at x equals 2 and x equals 3. That one was nice. We didn't have to graph it. All right, the next one, let's do that. So first of all, set your denominator equal to 0, which gives us x equals 2 as our point of discontinuity. Now let's figure out what is going on at that point. Set your numerator equal to 0, so x minus 2 times x minus 1. Solve that. And you may be able to see what's going to happen before it actually does and save yourself some work. X equals 2 matches, and x equals 1 does not match. I don't need to worry about that one. So since it's a match, we have to look at the graph to figure out what's going on. We could do this without looking at the graph by plugging into the equation and figure out what's going on close to those points, but that's a little more work than we need to do right now. So you can just look at the graph. When you put this in the graph, you're going to put the whole thing in the graph. Make sure that you put parentheses around the numerator and around the denominator. It will not work unless you do that. Well, it'll work, but it will not give you the correct graph. So pause the video and take a minute to graph that. Alright, if you graphed it correctly, it should be a straight diagonal line like that on your calculator. If it's not, pause the video again, go back and see if you can figure out what you did wrong. Now, do you see any extreme behavior? Is it going way up to infinity or way down to infinity at the 2, our point of discontinuity? No, it just looks like a normal graph. So what that means is that there's a hole at x equals 2. If you go into the table for this graph, you'll see an error at 2. Since the graph just looks like a normal, connected, straight line, there's a hole. All right, next one, we follow the same steps. So 1, set your denominator equal to 0. These two factors are going to produce the same 0, which is x equals 3, and the other factor produces x equals negative 4. Those are points of discontinuity. So we know our graph is funky at those points, but we got to figure out the type. So set your numerator equal to 0. These look like they're going to match up. See, that one will give us x equals positive 3. The next one is negative 4. So since they're a match, look at the graph. So make sure when you graph these that you put parentheses around the numerator and the denominator. You're putting these into the same y equals. It's all 1 y equals, numerator divided by denominator. Pause it and graph, and come back when you're done. This should be what your graph looks like. What is happening at 3? We have very extreme behavior. The graph is not a solid connected line. So that must mean that we have a vertical asymptote at x equals 3. If you want to, you can draw a dotted line in there so you see it. And then at negative 4, on your calculator, it doesn't even show the graph going all the way there. That's just because it's so close to the axis that it can't show it. If we had more pixels, then it would maybe show it, but our pixels aren't small enough. So, did you see any extreme behavior? Did it go way down or way up at -4? No, it didn't do either of those things. So, that means it must be a hole. Well, I was trying to get it to let me undo those blue arrows, but I'll just have to erase it. Okay, so hole. We can just say hole x equals -4. If it's not an obvious vertical asymptote, then it must be a hole. On the back of the notes, we're talking about horizontal asymptotes. For horizontal asymptotes, I like them better. I think they're easier. You actually just have to look at the highest degree of the variable on top and bottom. Then use the chart below to actually tell you where the horizontal asymptote is. So let me give you an example equation. Say y equals 2x to the 4th minus x cubed plus 2 and 3x cubed plus x squared minus x. Okay, I just made that up. What is the highest degree of the top? Degree talks about coefficients. The highest degree is 4 on top and the highest degree on bottom is 3. So our bigger degree is on top. So that means we're using this row here. Since our bigger degree is on top, that means there is no horizontal asymptote. I like to think of it as the big one eats the little one, so there's no little one left. There's none. Now let's go and look at this one down here. We'll just switch them. Okay, so let's make 2x cubed minus x, that's already there, minus 2 over 3x to the 4th plus x squared minus x. What's the highest degree on top? 3. What's the highest degree on bottom? 4. So now the little one is on top of the big one. That means the horizontal asymptote is y equals 0. The little one eats the big one and gets really fat, like a 0. Now the last one, this middle row here, is peculiar. This one is when your degrees are the same. So say it's 2x to the 4th minus 2 over 3x to the 4th plus x squared. Let's make that one a little shorter. When your degrees are the same, your horizontal asymptote is going to be their coefficients. These numbers right here. So the horizontal asymptote for this one is y equals 2 divided by 3. So when the leading coefficients, the highest degrees are the same, you take the leading coefficients. So that's the horizontal asymptote. That one probably happens the least. This one probably happens the most. So let's use this on example 3. Find the horizontal asymptotes of y equals 3x plus 5 over x minus 2. Are the degrees the same or different? They're the same because they're both a 1, an assumed 1. So we're going to take the numbers in front, which is 3 over 1, which reduces to just 3. That's your horizontal asymptote for that one. Next one, same or different? They are different. This one's a 1. This one's the one below is a 2, which means it's little over big. So what is the horizontal asymptote? Y equals 0. Now let's put it all together for this last example. Call this the big kahuna of the whole thing. We're going to sketch a rational function using the asymptotes. Let's find our vertical asymptotes first. So start by setting your denominator equal to 0. And finding the points of discontinuity. So our points of discontinuity are x equals -3 and x equals 4. Pause it and make sure you've got all the work, and that makes sense how we got that. Now we got to figure out the type. If we set our numerator equal to 0, is that going to match either of our points of discontinuity? No. No match means what kind of discontinuity? Means vertical asymptotes at x equals -3 and x equals 4. Go ahead and go graph those on this graph over here. So let's see, -3 and 4. Now let's find our horizontal asymptotes by looking at the degree. What's the degree of the top? It's 1. That x's exponent is 1. Now the degree of the bottom, that's not in standard form, so we need to get rid of those parentheses. So we have to FOIL. So first term times first term, it's x squared. Let's see, and then outside, inside, last. We're concerned about the leading coefficient. Okay, nothing else is higher than that. So we have 1 over 2, so that's little over big. So what is our horizontal asymptote? Y equals 0. You can go ahead and graph that. It's on the x-axis. Alright, so you see how the graph is going to be broken up. But what does the graph actually look like? Well, you need to look at your calculator. So graph original equation on your calc to get a rough sketch. Make sure you watch the calculator actually graph it. So like watch the order that it goes in, because you'll see that your calculator at -3, it gets close to -3 and then starts going down. Then from -3 on, it starts up high and then goes over to the 4 and goes down. Then from the 4 going on, it starts up high and then goes out to the right. So that's what your graph looks like. Horizontal asymptotes are weird because they don't always apply. So like it doesn't apply to this middle section, but it does to the 2 outside sections. I don't know why. That's just how it is. I'm sure there's reasons. I just don't know why. Okay, so you have 6 problems at the end of your homework that are graphing like this. The important part are the asymptotes and the holes. Make sure you graph those correctly. Then just make a rough sketch of the rest. It needs to be accurate, but it doesn't have to be 100% perfect.